going to say that a curve is closed when the beginning and the end of the curve coincide. So for instance, if this is the beginning and this is the end of a curve, so this curve is not going to be closed. But if the beginning and the end coincide, so this curve is going to be closed. And this curve, like this, is going to be closed too. So this will be closed, this will be closed, and this one will be not closed. And we are going to say that the curve is simple when this cannot happen except at the beginning and at the end. Meaning that if I have a curve that does this is not simple, because here there will be 2 points in which the values of the curve is the same, and they are in the interior of the interval, meaning they are not at the beginning or at the end, right? They are not at A or B, but in the interior. So this curve then will be not simple, and a curve like this, let's say, that will be simple. A curve like this will be also simple. So this one, for instance, will be simple but not close, right? But will be, both of them will be simple curves. Okay, so we're going to see this important theorem for line integrals called the Green theorem, that it says it provides another way to calculate a line integral of a vector field. Remember that before we have a way to calculate when the vector field is conservative. This is going to be instead for any vector field. And so what this result says is that if we have any vector field on a simple connected domain in which the domain is bounded by a simple closed curve. So meaning that if we have, let's say, a domain like this, so this is the domain in which the boundary, we see that is a simple closed curve. So we are going to say that the line integral of the vector field can be calculated also in this way. And this way is not a line integral anymore. This is just a double integral of a domain that in general is easier to calculate than a line integral. So this will be a double integral over the interior, let's say, what is enclosed by the curve, and the function that we're going to put here is going to be the partial derivative of n respect to y minus the partial derivative of n respect to y. So these are going to be functions in the real numbers, right? So here will be, this is a vector field, and these things that we have here are both functions with values in the real numbers. Some alternative notations that you may see for this theorem. So since the curve is closed here, sometimes this is written this way. I mean, with a circle in the integral. This is a notation that is used a lot in physics. So this is an alternative notation for this integral. Another one is to put the integral, and instead of calling C, since C is actually the boundary of this domain, you can put just this notation that means the boundary of D. So any of these two notations will be equivalent for the line integral here. And for the vector field, another equivalent notation is just to put the components of the vector field here, right? So we can put here m dx plus n dy. So this will be an alternative notation for the line integral. So for example, let's calculate the line integral of this vector field over this curve, where this curve is a circle of radius 2 centered at the origin. And we're going to use Green's theorem to calculate. I mean, we are not going to calculate directly by the definition, that is what we knew how to do before, but we are going to apply Green's theorem to calculate this. So let's do a drawing of the curve and the domain that enclose, right? That since both things are going to be needed. So in this case, it's a circle of radius 2. So this is going to be 2 here. And so the domain enclosed is going to be all the interior of this circle. So inside here, this is going to be the domain, and the boundary, this is going to be the curve. Okay, so the integral over c of f dr according to Green's theorem is going to be the same thing that calculate the double integral over this domain, right? The thing that is enclosed by the circle. And of what? Well, we have to put the subtraction of the cross derivative. Well, let's calculate this subtraction. So first, let's calculate the derivative of the second component here. The derivative in this case will be of minus x cubed with respect to x. So it's the derivative of the second respect to x, and the derivative of the first respect to y. So these are the two derivatives that we are going to need. So in the first case, the derivative of minus x cubed is going to be minus 3x squared. And the derivative of y cubed respect to y is going to be 3y squared. So then the subtraction that we have to write here will be just minus 3x squared minus this one, 3y squared. Okay, so now we have to set ourselves to calculate this integral. So remember the method that we had to calculate double integrals. So in this case, considering the domain is a circle, we like to do here a change to polar coordinates. Remember that for polar coordinates, we need to change x is equal r cosine of theta, y equal r sine, and we need to multiply the differential by r. So then this integral is going to be equal to the integral from the variation of r in here will be from 0 all the way to 2, right? So that will be from 0 to 2 r dr. This is the r belonging to the change to polar coordinates. And then we need to do the other variation, the variation of the angle, since it's the whole circle, is going to be from 0 to 2 pi d theta. And in here, we are going to change the variables by this. So the result is going to be minus 3x squared. This is going to be r squared cosine squared. Minus 3y squared. This is going to be r squared sine squared of theta. Okay, so let's do the operations and let's calculate these integrals in polars. So first of all, let's do the algebra here. We're going to get here minus 3r squared, and then we have sine squared plus cosine squared, right? So inside of the parentheses, we'll have just minus 3r squared, and then we have times this other r here. And so this is going to be the integral between 0 and 2 pi of the integral between 0 and 2 of this, which is minus 3r cubed dr d theta. And now we can take the 3 outside of the integral, the minus 3, integral 0 to pi, and let's integrate this respect to r. So this is going to be r4 over 4, evaluated between 0 and 2. So let's do this evaluation now. So that will be minus 3, integral between 0 and 2 pi, and we are evaluating this between 2 and 0. When we evaluate at 2, we get 16 over 4, which is 4 minus 0. And so this is the integral of 4. 4 goes out of the integral. Minus 3 times 4 is minus 12. Integral between 0 and 2 pi of just 1 d theta. So this is minus 12 theta evaluated between 0 and 2 pi, which is 2 pi times 12, which is minus 24 pi. So that will be then the result of the line integral that we calculated without doing any line integral, right? But doing a double integral according with Green's theorem.